Hey friends, good morning. So today we will be talking about a rate limiter and we will design a rate limiter system. So we will briefly talk about what is a rate limiter, what are the benefits of rate limiter, and then we will discuss some questions. We will clarify the requirement. So whenever you are in an interview and you have to design a system, we should first discuss with interviewer what are the requirements that I'm going to design a system for, and then we will log that requirement. So there are some functional requirements and there are some non-functional requirements that we want to consider while building a system. So interviewer and the candidate both should agree on a final set of requirements that these are the functional requirements and these are the non-functional requirements that we should consider while designing a system. Then we will talk about a high-level design and we will then talk about algorithms. So before moving into the complete design, we will discuss the algorithms that should be used, that can be used to design a rate limiter. So there are five algorithms that can be used to design a rate limiter. The first one is token bucket. Second one is leaky bucket. The third one is fixed window counter. Fourth is sliding window log. And the fifth one is sliding window counter. All the five algorithms have some pros and some cons. And depending upon our use cases, depending upon what we can afford and what we cannot afford, we will choose one algorithm to design the rate limiter. And then we will discuss the complete design. After that, we will move to the distributed environment. So it is very important to consider a distributed environment because it is easy to implement a system for a startup, for a small company, and when the audience is small. But when we think about the big company, the big organization where there are many clients sending a too many requests to a system, it is very important to consider the distributed environment. And at last, we will talk about the failures, how we should handle the failures. So no matter how perfect we will design a system, there can always be a chance that the system can break. So how we should handle that? One failure could not impact the performance of entire system, and therefore we should have some technology, some workaround to handle those failures gracefully. So let's move ahead and first discuss what is a rate limiter. So we will first discuss what is a rate limiter. So let me write it down. What is a rate limiter? So a rate limiter is a system that controls how many requests a client can make to a particular server. So I'll write it down here. So it is a system that controls how many requests a client can make to a server in a given time window. For example, there is a client and there is a server. This client wants to send some HTTP request. So before sending this request to the server, there might be a rate limiter which will actually decide if this particular request should go to the server or not. So, and this rate limiter decides this based on some predefined limits. So, for example, there is a payment service, and we have a limit on that payment service that in 1 minute only three requests, OTP requests can be served. So, clients can request for three OTPs only in 1 minute. So, this rate limiter will track the number of requests that is being sent by the client in a minute. And if the request exceeds this three limit, that request will be blocked and will not be sent to the server. Another example can be in the authentication service. Let's say the the limit has been defined that the client can only make 5 tries, or the 5 times he can log in. He can make a request to log in 1 minute or in 1 hour to this system. Uh, Another example we can think about is Facebook. Let's say Facebook has a limit that a particular user can only add 500 friends in 1 day. This is not an actual data that I am aware of. I'm just giving some approximation, some data to understand that Facebook can have such limits that Only a friend can make, let's say, 5 posts in a day, in 1 hour. He or she can add only 500 friends in one day. If the user wants to add more friends, he has to wait for next time window, which is the next day. So this is how a rate limit. This is what a rate limiter is. Now let's talk about some benefits of having a rate limit. Okay. So what are the benefits of rate limit? So the number one, it prevents resource starvation. So sometimes resource starvation is caused by denial of service. And in that cases, having a rate limit is a good idea. It prevents the resource starvation. The second is it prevents overload. So if there are too many requests in a short time interval coming to our system may get overloaded, and it can impact the health of our system in production. And therefore, we should have a rate limiter which can limit the number of requests coming to our system. The next benefit of having a rate limit is ensure fairness. So there are 100 clients, let's say, they are sending some requests to our service. It can be possible that 10 of the clients are making too many requests to our service, and they are impacting the availability of the service for other clients. So by limiting the number of requests for each client, we are actually ensuring that all the clients will get the resource availability. Then we will talk about prevention of abuse. So sometimes having a rate limiter is a blessing to avoid any kind of abuse, any kind of malicious attack on our system. For example, let's say someone who is not authorized to log in into our system, but they are trying to crack the password through brute force approach. They are trying to guess the password by making some multiple attempts. So in that case, having a rate limit that you can only try 3 times in a minute, we are actually blocking those users to cracking the password. So we are actually preventing someone who is not authorized to log in into our system to log into our system. The next benefit of having a rate limiter is cost control. So usually in case of a paid service, using that service unlimited can impact the cost. Cost can be higher, especially in a organization who is using a third party paid services. They try to have some limits on the usage of that service so that the cost can be reduced. So these are some of the benefits of having the rate limiter. Now we understand what is a rate limiter and we understand what are the benefits of rate limiter. Now before designing the rate limiter system, let's discuss some questions and then we will move to the design. So it is always a great thing to clarify your doubt, to discuss your questions with the interviewer before designing the system. So your question can be to the interviewer that who are we limiting? Who are we rate limiting? Is it user ID? Is it IP address? And is it API key? So this basically user ID or IP address or API keys are the unique identifier for a client, can be unique identifier for a client. And these identifiers can be used to rate limit. For example, this user already sent me 5 requests. I am not going to allow this user ID to send more requests or process any more requests from that user ID. Or maybe this IP address, I can use this IP address as a identifier to identify a particular client, and I'll prevent more than 5 requests from this IP address. Similar for the API key. API key can act as a identifier for a particular client. Interviewer can directly ask you to consider user ID as a unique identifier or API key IP address as a unique identifier, but He or she can also ask you to design the system that should be configurable enough, that should be flexible enough to support all any of these identifiers to identify a client and limit the number of requests that the client can send to the service. Okay. Once we get, then we can move to the next question. You can ask your interviewer what kind of service that you are going to design, kind of system. Is it server side or client side? Client side versus server side. So usually having a rate limiter on a client side have some downside because you might not have access to the client side implementation, and therefore it might be a better idea to design a rate limiter on a server side. Third approach can be to have a rate limiter as a middleware. So you have a client, you have a server, and in the middle, as a middleware, you can have the a rate limiter. When the request comes from the client, it will first go to the rate limiter. Rate limiter will decide if this request has should be forwarded to the server or is it or should it be dropped. Okay. So we should also discuss with the interviewer, are we going to design this for a startup or a big company? Obviously, you will be asked to scale the system for the big company. Then you can say, you can clarify some more questions. You can ask some more questions that is the rate limit same for everyone, same for everyone, same for all API endpoints, or it can be different. Actually, even interviewer can ask you these questions. Are you going to put in your design same rate limit for everyone, same rate limit for all the API endpoints, or different rate limits? It is always good to have that kind of flexibility, that kind of scalability to consider different rate limit for different endpoints. For example, as we mentioned, some sensitive API like payment app, authentication service, which are very, very sensitive, can have a very low limit. Only 5 requests in a minute, only 3 requests in a minute. But non-critical APIs like service which are providing the weather information can accept multiple requests. So request can be limit can be different for the different API. Is it same for everyone? It may or may not be. It depends on our system performance. For example, uh, in one location, our service is running on two particular location. Let's say location A and location B. In one location, we usually face overload on our system. However, on another location, our system is running very healthy. So where we are having a problem of overload, we can try and put a smaller limit. Only 10 requests can be accepted in this location because my system is getting overloaded again and again. On the other hand, on another location where our system is running perfectly fine, is in a healthy state where we can increase the limit. 20 requests can be accepted, 30 requests can be accepted. So depending upon our system performance, depending upon our use cases, the rate limit can be same for everyone. Rate limit can be different for everyone and different for all the APIs endpoints. Okay, so let's move ahead and log our requirement. So I am going to design a rate limiter with this functional requirement. So the number one functional requirement is system should be able to determine if a particular request should be accepted or rejected. It should it allow or reject a request. Then system should be able to support different rate limits for different API endpoints for different use cases. Then it should be able to identify a client through a unique identifier with its user ID, IP addresses, or API key. It should be flexible enough so that it can be scaled based on the user ID, based on the IP address, or based on the API key to identify a particular client. Then it should return, uh, it should inform client that your request has been throttled, which means send a 429 HTTP response to the client in case their request is dropped. This 429 HTTP response indicates that you are sending too many requests to the service and no more requests can be accepted in this given time window. Now, these are the functional requirements that you are going to design the system for. Now, let's consider some non-functional requirement as well, which are equally important. In the non-functional requirement, we should talk about scalability, availability, then you should talk about consistency. Your system should have low latency. Having a rate limiter should not impact the overall performance of your system. And also, the last thing, it should be able to handle failures. So these are some of the functional and non-functional requirements that we are going to consider while building a rate limiter. Now, let's quickly talk about a high-level design. So as we mentioned, a rate limiter can be designed on a client side, it can be designed on a server side, or it can be designed as a middleware. Designing a client side is a bit tricky because, as we discussed earlier, you may not have access to client side implementation, and in some cases, even the limit on the client side that has been put on the client side in a rate limiter, which is embedded in the client side, can be forced. So, client side implementation, let's avoid it. So we can design as a middleware or we can design as a on a server side. Or generally nowadays, lot of cloud providers, the cloud microservices have a rate limiter in the API gateway. So it is also a better idea to have a API gateway and let's have rate limiter embedded in the API gateway. So our high level design will look like something like this. So there is a client sending some request through his mobile phone or laptop or desktop, etc. So this is a client. There is this API gateway through which a request will go to the backend server. And in that API gateway, there is a rate limiter which has been embedded, implemented. Then you have backend service. Now, a request comes to this API gateway. Since API gateway has a rate limiter embedded in it, it will rate limiter will determine if this request should be forwarded to the backend server or not based on a counter. So there is a counter which is stored in a database which is in memory cache, let's say Redis. So Redis is storing a for each of the client, counter for each of the client, which tracks how many requests has already been sent by this client to the service. And based on that counter, this rate limiter will decide whether this request should go to the backend service or not. If the number of requests already exceeds the defined limit, then that request should be dropped, should not go to the backend server. If the number of limit is greater than the number of requests that has already been processed, then in that case, we can forward this request to the backend service. So this is a pretty much high level design. We will discuss more about this in a complete design. But before that, let's discuss some algorithms that can be used to design the system. So there are five algorithms that we just just discussed. The number one is token bucket, two is leaky bucket, we have third fixed window counters, then we have sliding window counters, sliding window log, and then we have fifth one, the sliding window counters. Now, each of these five algorithms have some pros and cons. Some have the memory issues, some consumes a lot of memory, some are memory efficient, some has some traffic spike issues, some are not very accurate, and etc. So we will discuss briefly what these algorithms are, what are the pros and cons of these algorithms, and then we will try to choose one best algorithms to design our rate limiter. So we have a token bucket. So what is it? So it's like there is a bucket and it has some capacity. So let's say it the maximum size of this capacity is 4. That means this can have at max 4 token. And if we will try to insert more token into the bucket, that will overflow. Now there is a refiller which will fill this bucket with token. Let's say every 15 seconds, one token every 50 seconds. But this bucket can accept token only if there is an empty place. If the bucket already has 4 token and the maximum size of the bucket is 4, then it cannot accept more token from the refiller. So token bucket has two parameters. The first one is bucket size and the second one is refill rate. So in this example, we can take bucket size 4 per minute and the refill rate is equal to 1 token per 15 seconds. So in every 15 seconds, this refiller will try to insert one token into the bucket. And if there is a empty space in a bucket, the bucket will accept that token. Otherwise, it will overflow. When a request, each token will be corresponding to one request. When a request comes from a uh, client send a request, it will the rate limiter will try to check do we have a token in the bucket? If there is an available bucket, then that request will be forwarded to the backend server. If there is no token available in the bucket, that request will be rejected. When we will discuss about pros and cons of this one. So the pros is this is memory efficient. This is simple to implement and understand. And this also supports allows a burst of traffic for a small amount, for a small period of time. When we will talk about some cons, so since there are two parameters, it might be tricky to tune the both parameters. So this is the cons of this token bucket algorithm. Otherwise, this is very simple, memory efficient, easy to implement, and it supports a burst of traffic, which is actually required for a real API. Okay, let's talk about next algorithm, which is leaky bucket. So this works in the same way as token bucket works. So it also has a bucket size and bucket size, but the only difference is which can take a maximum number of tokens, or let's say not token. There is a size of bucket defined, and it can take only that number of requests. So the difference in leaky bucket and token bucket is that there is a queue in this scenario, which is actually equal to queue size you can say the queue size is equal to bucket size. And let's say in this case we have a queue size for 6. What it means is when a request comes from a client, the rate limiter will check if do we have a space in the queue or not. If there is empty space in the queue, that request will be uh, put in the queue. Let's say we put multiple requests in the queue, and at a fixed rate, all these requests will now be taken and processed at a later time. So the first requests are put into the queue. Let's say six requests has been put into the queue, which is equal to the bucket size, and then those requests will be taken out from the queue at a later point of time, and then that will be processed. That processing time is fixed. I mean, there is a fixed rate of processing time. So the problem with this is also memory efficient, and but this uh, does not allow burst of traffic because the requests are processed at a fixed rate. Let's say every 2 minutes, two requests will be taken from the queue and that will be processed. Now, in the next 2 minutes, the two requests will be taken and processed. So, there is no burst of traffic in leaky bucket algorithm. The problem with this is when we will talk about the cons. Let's say it also takes the two parameters as we discussed. There is a queue size which is equal to the bucket size, and the second parameter is first parameter queue size, and the second parameter uh, rate fixed rate of rate of processing the request. If these two parameters are not tuned properly, what will happen is uh, a number of old requests are being filled into the queue, and all the new requests will be dropped off. So basically, we are dropping off all the new requests because the queue is filled with a lot of old requests. So this is one of the major problem in leaky bucket. Okay, let's move to the next algorithm, which is fixed window counter. So in this algorithm, what we do is we will try to define the time window. We have a fixed time window, multiple time window, and length of that time window is same. For example, here there are four time window. Each has a length of 1 minute. 1 minute. This also 1 minute. This also 1 minute. Means if we'll start with a 0 minute, the first time window will end at 1 minute. Second will end at 2 minute, 3 minute, and 4 minute. 4 minute. So we have a fixed time window, and we have a limit on each time window that one time window can process four requests. So the four requests can be processed in one time window. To process any more requests, clients have client has to wait for the next time window to start. So in here also the four requests can be processed. In this time window also the four requests can be processed. In this also the four requests. When we'll talk about pros of this, so this is also a very memory efficient algorithm, and this is also very simple. We have to define what is the size of the time window and what is the number of requests each time window can process. The problem with this is when we will talk about the cons, the problem with this is a spike of traffic at edge of the time window. So for example, let's say in the second time window there was no request processed till 1 minute to 1 minute and 50 seconds. 1 minute and 50 seconds, no requests were processed. But in the last 10 seconds, we processed four requests. Again, in the start of the third window, we processed all the four requests again in just 10 seconds. And again, in the next 50 seconds, two requests were processed. So, just in 20 seconds, eight requests from a client was processed, which already violates the limit of having only four requests in a minute. So there is a spike in traffic as is of the time window. Okay. So we also talked about fixed window. Let's move to the sliding window log. This actually solves the problem of fixed window counter. So fixed window counter, as we saw, there is a spike of traffic at the edge of the time window. What sliding window does is we are sliding the window. So in any 1 minute, 1 minute to 2 minutes, 1 minute 10 seconds to 2 minute 10 seconds, 1 minute 30 seconds to 2 minutes 30 seconds. In any 1 minute of time window, only four requests can be processed, and there will not be a spike in traffic in case of a sliding window log. So this algorithm is actually very, very accurate. You can take any 1 minute and only four requests will be processed. How it does this? It tries to it stores the timestamp of the request at what particular time a request arrives, and from that to next 1 minute, only four requests can be processed. So at any given point in time to the next 1 minute, only four requests. For example, let's say request one arrives at 1 minute and 10 seconds. Request two arrives at 1 minute and 30 seconds. Request three arrives at 1 minute and 50 seconds. Now, request four arrives at 1 minute and 55 seconds. 55 seconds. Now, all the four requests are done. When I start from here and till 2 minutes and 10 seconds, which is a 1 minute length, only four requests can be processed, and four has already been processed. No more request will be processed. But as soon as we will move to 2 minutes and 20 seconds, uh, what was what is the current window? It should be from 1 minute 20 seconds to 2 minutes 20 seconds. So we will delete all the requests which are not in this window, which means this is already outdated and do not does not fall into this limit. So what it means is only three requests has been processed, and we can still process one more request. So this is how it works. It deletes the outdated timestamp, and it try to count how many requests has been processed from now to the 1 minute before, and how many requests can still be processed. So it actually solves the problem of having a spike at edge of the window and violating the limit size. It is very accurate. The problem with this is very memory consuming. So it is storing the timestamp of all the requests, and because of that, it consumes a lot of memory. Now, to solve this memory problem, we have a next algorithm, which is a sliding window counter. So this is actually a hybrid of a fixed window counter and sliding window log. So this is fixed window counter has a problem of a spike at edge of the time window, and sliding window counter has the problem of uh, consuming a lot of memory. So this sliding window counter does not store the timestamp of the request, and therefore it does not consume a lot of memory, and it works on the approximation. It does not work on the actual defined limit. It try to approximate the number of requests, approximation based on current window and previous window, and then it works on the approximation, and therefore it avoids the traffic spike at edge of the window time window. But as we mentioned, the problem with this is a approximation, just the average uh, limit, not the actual limit. So it only works on not so strict scenario. So we discussed all the five algorithms. We discussed um, token bucket, we discussed leaky bucket, we discussed fixed window counter, sliding window log, and sliding window counter. Now, we also discussed what is the problem with which window. Now, let's choose one of the algorithm which is most suitable to our requirements. So, uh, uh, if we'll talk about token bucket, it has a problem of tuning the two parameters, which is bucket size and the refill rate. If we can tune the two parameters and we can ensure that it will not cause a lot of problem, then we are good to take to choose token bucket as our algorithm to design a rate limiter. If we'll think about leaky bucket actually does not support the burst of traffic, and therefore uh, we may want to avoid it. When we will talk about a fixed window counter, as we discussed, there is a spike of traffic at the edge, so which may cause overload on our system. When we will talk about sliding window log, it consumes a lot of memory, but it is very accurate. If we can afford memory, then we are good to choose sliding window log. Sliding window counter is has a problem of approximation. It does not work with the actual limit. So, in my opinion, you can choose any one of the algorithm to design a rate limiter. But in my opinion, let's choose a token bucket. And we already discussed the trade-off. Why we are choosing a token bucket, because all other four have some kind of problem which we do not want to afford. Is, for example, memory issue with the sliding window log, a spike, traffic spike with the fixed window counter, approximation rate on the sliding window counter, and the no support for burst of traffic in the leaky bucket, or uh, when the older requests are uh, inserted into the queue, all the new requests will be dropped out, which is not a good idea to have a rate limiter for. So we can on the basis of these trade-offs, we can choose token bucket to design our rate limiter. Now, let's discuss and design a uh, draw a complete design for our rate limiter. So I'll quickly draw a complete design for a rate limiter that we are going to have for our server. So there is a client, and this is a client. There is a API gateway. There is a rate limiter embedded into it, and this is backend server. Now, client sends a request to the API gateway. API gateway is embedded with rate limiter. Rate limiter will query Redis, which stores the counters, which tracks for each client. Key is your client ID, and the value is your number of requests that has already been processed. Let's say 5. Now, we have this uh, information stored for each client into the Redis. We took Redis because Redis is a in-memory cache and which is very fast and efficient. If we store this data into the disk, accessing any data from the disk is a very slow process. And if rate limiter is going to access data from the disk, it will already slow. It will slow down the performance of our entire system, which we can't afford the performance of our system. So therefore, we will avoid storing any data in our in disk. Instead, we will store in the Redis. Now, we have a rules defined. What are those rules? So we have a rules like rules of rate limiters. Like let's say for a payment system, we are defining a rule. So domain, we are saying payment application. Then we are describing. We have in the description. We will say um, key payment type value, uh, let's say the rate limit for this payment type. Now under the rate limit, since we are building based on the token bucket algorithm, so we will define our bucket size, let's say 4 per minute, and also we will define the refill rate which is one token per 15 seconds. So these are the rules that we have defined for a rate limiter based on the token bucket algorithm. And these rules are stored into a cache. So actually, this is not stored into the cache. We can store this into a disk. These rules are stored into the disk. But as we mentioned, accessing something from a disk is a slow process. So if rate every time rate limiter will go and access the rule, the defined rule from the disk, it will be a very slow process. So to avoid this, we will design a worker which will at certain interval it will try to pull the rule from the disk and it will store back into the cache. So so that the rate limiter can access this rule from the cache faster. So rate limiter will get that is stored into the cache. Rate limiter will fetch counter that is stored into the Redis, which is in memory cache again. And based on this rule, based on this defined limit, which is bucket size 4 and refill rate 1 token per 15 seconds, based on this and based on this counter, we have implemented this rate limiter uh, based on the token bucket algorithm. And after doing the process, it will decide should we allow this particular request or not. If yes, then send this to the backend server so that backend server can send HTTP response back to the client. If no, then drop this response, this request. So this is in a way a simple system design diagram for a rate limiter. Now, as we discussed that building a system for a small startup, a small company is fine, but we should have a flexibility to scale that for a big company. And if we are designing a system for a big company, for a larger audience, we should think about distributed system. When we will think about distributed system, usually two issues arises. The one is race condition, and the second is synchronization issue. So we will understand this through an example. So when we're talking about distributed environment, there are multiple instances of API gateway. API gateway 1, let's say, and we have API gateway 2. Now, there is a client 1 and there is a client 2. This client sends a request to the API gateway 1. This client sends a request to a API gateway 2. It sends a request R1, it sends a request R2. Now, this a both API gateway are embedded with rate limiting algorithm. So rate limiter will decide if this request will go to the backend server or not. But since the servers are stateless, what it means is any client can send the request to the any rate limiter or any API gateway. Let's say the next time client 2 send a request R2 to the gateway 1 and client 1 send a request another request R2 to the gateway 2. What will happen is API gateway 1 will not know what was the counter, the previous counter for client 2, or API gateway 2 will not know what was the counter for gateway for client 1. So how they will determine which request from C1 or request from C2 should be allowed to the backend server or not. You can say that just have this asterisk session and request from C1 can only be sent to the gateway 1 and request from C2 can only be sent to the gateway 2. But this is not advisable because this is neither scalable and not flexible. One client cannot be only sending the request to a particular gateway because this way we are actually violating the law, the idea of scalability. So what we will do is we will have a instead of having separate database for each of the server, we will have a shared data, centralized shared database for all the API gateway. So any API gateway, this will store the information of client one, client two, and all the clients. What are the counter and etc. And any API gateway can query this shared source of truth, the database which is a shared source of truth, and they can actually know what is the counter, what is the current counter for a particular client, and depending upon that, they will determine whether this particular request from a particular client should be sent to the backend server or not. This is a problem of synchronization, and this can be solved with a shared source of truth database. Now, when we'll talk about a race condition, let's say we have a counter, global counter, uh, and there are two concurrent requests that comes in. Two requests simultaneously comes. One request comes to the API gateway 1, and another request comes to the API gateway 2. Now, they both will try to read this counter from the their data, and they'll both, let's say the initial value of this is 3, so they'll both try to increment it to the 4. Actual, because two requests are going to be processed, the final value of the counter should be 5. But since both are in a race condition, they are trying to update it from 3 to 4. This is not correct. So to avoid this, what can we do? The simple solution is, let's have a lock and apply lock until one request is processed. Then release the lock and process the next request so that we can have the correct counter value, which is 5 and not 4. This will actually slow down the process. And therefore, we have another solution for this, and which is called solution for race condition, sorted state data structure of Redis. So Redis support a sorted state data structure. What it does is, when two people have the same value, it will try to add some unique identifier, and both entries will be added into the sorted state, into the state. And instead of, so let's say there were three entries already, one, two, three, and two APIs are trying to make it to 4 instead of 5. So let's say we have 4, we have again 4, but this entry will have some kind of unique identifier so that this can be identified that these are not the same entry. These are two different entries, and based on that, when we will calculate the size of the state, it will not be 3, but it will not be 4, but it will be actually 5. So this way, the race condition can be solved in a distributed environment. Now, the last part, let's quickly talk about failures. So, as we mentioned here, in the as we mentioned here, in distributed environment, we are going to have uh, shared data, centralized data for all the API gateway instances. So, there is a bottleneck. This is a single point of failure. If this cache server goes down, there will be single point of failure, and none of the API gateway should work properly. Then what is the solution? The solution is, uh, we will try to shard the database, shard database, and so that counter for one client, counter for one client can live only on one shard. Now, we should also have replicas of shard so that we can avoid the single point of failure or the bottleneck actually. So it can have one primary shard for write operation and multiple replicas for read operations. So this way, we are actually going to solve the problem of bottlenecks and single point of failure by starting the database and having replicas of each of the sort. But let's say in some scenarios, cache server is down, and what we will do, an API gateway is unable to read the current counter for a client from the database. Then what it will do? How API gateway is going to determine if this particular request from a client is going to be processed, should be processed or not. So in that scenario, what we can do is uh, let's discuss about two terminology. One is fail open, and the second is fail close. Fail open means for non-critical API, for non-critical API, if we don't know what is the current counter and we are unable to determine, the rate limiter is unable to determine if this particular request should be processed or not. For non-critical API, it will just allow and forward the request to the backend service. However, for the sensitive API, which are payment API or authentication service, it will not allow. It will just deny. It will say your request cannot be processed. So this is how we can handle the failures in our uh, system design for rate limiter. All right.